Hello everybody and welcome to my channel. This is Sohini from South Bay, California, and I welcome you today. Today's topic is data augmentation for machine learning, best practices explained with examples. We will be reviewing two major entities. One is output metrics and second is the parameters that are useful in order to ensure your machine learning algorithm is the best possible version that you can get. In this example, we will be looking at medical image segmentation. If this is of interest to you, stick around and subscribe to this channel. Additional teaser for next week. We will be reviewing the impact of dropout on convolutional neural network segmentation models, and also we would be learning how could we use the same model that we have trained on grayscale images and translate them for RGB or color images. Interesting, right? So stick around. The first and foremost important thing about machine learning is you need to understand that there are three sets of data that you should have. One is the training data, one is the validation data, and one is the test data. Now the training data is going to have your X and Y. X is each and every image, and Y are the labels that it carries with it. But whenever you're tuning the parameters for your model, you need another set of data in which you actually have the Y set of labels. So in this case, we call that validation data set. So validation data also has set of X's and Y's, which is my labels. So essentially what we are trying to do here is we are going to be using the training data set, which we knew there was 30 images in all. So we're using the first 20 for training, and we are using the last 10 for validation in this case. Ideally, if you're doing a rigorous machine learning experiment, these 20 and 10 should be randomly generated, and you should do enough iterations of this randomly generated training and validation data so that you do not have overfitting in your case. So far, so good. So we are doing semantic segmentation of medical images. Now, the first and foremost, in order to understand the importance or the improvement that is caused by the data augmentation, we need to understand output metrics. Now, the output metrics, it's a good blog that defines all these output metrics that I'll be linking in the description box below. But let's look at what it actually means. So whenever you have an actual region of interest, which is cell membrane in this case, and your algorithm is also segmenting cell membrane, then what you have is prediction, and then of course there is ground truth, which is the actual hand labeled region. Now precision is the metric which measures how much out of all that you have predicted is reality, is true. And recall says out of all the regions of interest, or out of all the pixels that you were supposed to classify, how many did you classify correctly? So that's why precision is true positive over true positive plus false positive, while recall is true positive divided by true positive plus false negative. So you see, one is the ratio with respect to false positive, the other is with respect to false negative. And of course, accuracy is just true positive plus true negative divided by all the pixels. And then you will have the F1 score, which is just the twice the true positive divided by all of true positive plus false negative. So these are the different metrics there that are used. Now let's go to the coding part and see what we have. With me so far? So this is the same folder that we looked at on our Tuesday session for data augmentation, and with just a few minor changes that I wanted to show you. Now we're looking at evaluation, or your output metrics, right? So with regards to that, I've generated this new file which is called evaluation.py that uses, first of all, we use the scikit-learn, and in scikit-learn there is this function called confusion matrix, where this can automatically return to you a list of the true positive, true negative, false positive, and false negative pixels. Now, what I then do is once these pixels are evaluated, then I'm able to generate the metrics that I just talked to you about. So the precision, the recall, the IOU, and then there is the F score, right? And then all I do is I compute everything together, and it's just returning. So this file I will be putting in the week 3 folder in the Google Drive for anybody to use as they may please. Now, what I wanted to show you is in terms of this output metric, which is in this case the precision recall and the accuracy and the IOU and the IOU and the F1 score. Now let's see what is the impact of the network parameters on it. Now, the network, as you know, in this case, the model, it's just a unit model. Again, it starts with a 256 by 256, and it goes through 4 layers of convolution and pooling, and then it goes through your up pool, right, followed by your final classifier. Now in this case, the parameters that we are looking at is, first of all, the learning rate, which is 10 to the minus 4, and the error, the error metric or the loss function that we have. So in this case, we are looking at the loss function, which is binary cross entropy, and what we are reporting as the final accuracy parameter, as the metric, which we are seeing as every single epoch is progressing. So ideally, as your epochs progress, you want to see the loss function reduce, and you want to see the metric go up, and that is what the outcome we require from this case. So what I'm saying is, if this is the standard metrics that came with the code base, that is, it had a learning rate of 10 to the minus 4, binary cross entropy, and with accuracy, we are interested to see that with respect to the output metrics that I just showed, what is the outcome. So I already have run it using the standard parameters that we had already. So understand, in this case, the parameters were just the learning rate and the loss function. So if we just had that particular loss function, and here in this case, I'm running it for 20 epochs for so of 20 per epoch and for 5 epochs, then you will see that the loss function keeps reducing. Of course, the accuracy is going up higher and higher and higher. So you are on the right trend for this case. Interesting, right? As a final step, we will now be looking at the impact of the data augmentation parameters. That is what we saw in our last session. So the rotation range, the width range, the shear range, and everything. And we will see its impact in terms of the quantitative measures that we have come up with, or the output metrics, and also qualitatively. So let's look at, I've already created an example of all the results that we have, and let's take a look at it quickly. So first thing is, let's look at the first case where we have a huge range for rotation, and also we have a larger range for your width, height, and shear. And here we are doing filling based off of the nearest neighbor method. So the thing to notice here is, in these cases, you will have these fringing in the edges, and that'll be a lot just because of your width and height shift is given a larger range. And in this case, I'm using again the cross entropy loss function and accuracy as the metric. And again, steps per epoch is 20 because I have 20 training images, and I'm running it for 10 epochs. In this case, I end up getting a recall of 85% and accuracy also of 85%. So let's look at qualitatively. So that was the quantitative results. This is the qualitative outcome. So if this was the validation image, you have the ground truth on it, you will see that these come out as false negatives. So, and I'm calling them false negatives because ideally these should have been, white. But ideally, if you threshold this image at a pixel value of 0.5, these regions will come out as pixel value 0. So ideally, it should have been predicted as pixel value 1, but it is getting predicted as pixel value 0. So that's why these become false negative, because of which there's a high false negative range, and the recall value is low in these cases. So ideally, you need to have a good semantic segmentation that would get rid of these false negatives altogether. Now let's look at another case where I kept the rotation range somewhat lesser. So the previous one, it was zero point 0.3, and now I'm keeping all the other ranges pretty small. So I'm not allowing very high fringing, very, very minimal. And again, these are the different augmentations that is being produced. In this case, again, steps per epoch is 20. And what the number of epochs I have is 7, because after 7, I saw that the loss was actually not improving anymore. And in this case, I was able to get a recall of 92% and accuracy of 87%. So definitely there is a gain. So what we're learning in this case is you shouldn't go overboard with this rotation range and the width range. Otherwise, you will get too high a fringing, which actually does harm to your overall segmentation than help it. So let's look at the outcomes in this case. Again, if you're looking at the same validation image and the ground truth, now you see the edges or of the false negatives are somewhat blurred, right? So you're not seeing as many false negative pixels, and that's why your performance has improved. Now I looked at another case, which was again going a little bit, it's like a middle ground. So not going overboard with some parameters and then going overboard with others. So if I take a rotation range, which is pretty high. So what is rotation? Rotation, when I'm rotating the image, around the center by a certain number of degrees. So the rotation range is high. Width and height, but in order to reduce the fringing effect, I've kept that pretty low. But shear and zoom, so I am able to now zoom in and zoom out. So if you look at the same region, this is like a zoomed out version, and this is more of a zoomed in region of interest. So this would be a third kind of augmentation where your rotation range is overboard, but you're keeping very tight limitations on the width and the height range. And again, this was run on 20 epochs with 20 images per epoch, and then on 10 epochs. And in this case, we saw actually the highest recall, which is 95%, and accuracy of 88%. And let's look at the prediction. So if your validation image is this, ground truth is this, you see now it is giving you the most blurry the edges for your the false negative. So this has the lowest number of false negatives, and that's why the recall is the best in this case. So I will be uploading these slides along with the Python files in the Google Drive for you to check out and utilize at your own time. Thank you. See you next time.